Okay, now another way of representing this idea of equilibrium and reversible reactions and then this position is talking about concentration. Okay, so if you take a look, when you talk about equilibrium position, we want to know which of the sides have a larger concentration, because this stuff is done in solution for the most of the time or with gases. Okay, so if you take a look, we have reactants we're representing as A, products we're representing as B, and we use these arrows. Notice how we make this arrow really long. We make this arrow really long going the other direction. So we use the arrows that kind of give us a visual. If you use a long arrow that's pointing towards the products, that means it's product favored. If you use a long arrow pointing towards the reactants, that means it's reactant favored. But anytime you see a double-headed arrow, it means you can have an equilibrium. So we use that whole double-headed arrow as an equilibrium indicator in our chemical reactions. Okay, this is not new. We've talked about it before, but we haven't talked about it for probably a month or so at least in terms of the double-headed arrows. Okay, so product favored versus reactant favored. Now, sometimes people get this misconception that a catalyst can change an equilibrium, and it can't. Okay, remember, catalysts only change the speed at which things go on, so it doesn't affect your amounts of reactants and products present. It only affects the time it takes to get to equilibrium. So if we back up to this graph, it would not affect any of these lines in terms of where they end for a catalyst. All it would affect is where this point is. So this point here would just shift further to the left. It'd be faster. So it'd get to equilibrium faster is all it would do when we deal with our catalysts. Okay? So that's what catalyst does for us. Now, if you're looking at equilibriums and you want to actually start to quantify it, okay? So if you're going to establish an equilibrium, you have to have a way to mathematically determine, well, where's that equilibrium going to sit and how much product am I going to make versus how much reactant do I have left over? Okay? So we do have a pretty quick way to actually calculate that. To do that, we talk about equilibrium constants or quantifying equilibrium. Okay? So your equilibrium constant, we say KEQ. Okay, K in the chemistry world is always some sort of constant. All right, so in our last unit, we had the boiling point constant, we had the freezing point constant for colligative properties, and they were K values. Same idea here, where we have a K value, and then EQ stands for at equilibrium. Okay, and what it does is it basically gives us a ratio of the product's concentration compared to the reactant's concentration. Now notice how concentration is in bold here because we're talking about molarities, okay? So it is the concentration of those. So it has to be a gas or it has to be in solution. We're not talking solids and liquids here. We're talking solutions or gases for concentration, okay? Now the way that you actually calculate this equilibrium is we do what we call an equilibrium expression, okay? Or we basically solve for KEQ. Now that ratio we always take to find our constant is we take our products concentration divided by the reactant's concentration. Okay. Now notice how I use a bracket here. Bracket is not parentheses, it's actually a squared off bracket. That bracket is a shorthand notation for concentration. So it's a way of actually labeling like molarity as a concentration without having to put the capital M everywhere. Okay. And the reason why we do it is because this expression is independent of what type of concentration you're using. So it could be molality, it could be molarity, it could be percent by mass, percent by volume, parts per million, parts per billion. It could be any type of concentration as long as you're comparing those two products to reactants ratio. Okay. Now this right here doesn't give us a whole lot of information. It just says take your products divided by your reactants. But the reality is we have reactions that are more complex where we have two different reactants, two different products, we have coefficients out front, so we had to basically, what does this mean in terms of actually breaking it down mathematically? Okay, so first thing we want to make sure we understand is in yellow here, the A, the B, the C, and D, that represents the coefficients from a balanced equation. Okay, so this would be like a 1 up front, or a 3 up front, and a 2 up front, and a 3 up front, that kind of stuff. That's what these are. We have our double-headed arrow to indicate equilibrium. So we know we have an equilibrium. Now to build the concentration, or the equilibrium expression I should say, what we do is we take our products, so our products are C and D, and we want the concentration of those, so that's why we have those in brackets. So what is the concentration? This will be a number, like a molarity, like 0.2 molar or 3.5 molar or whatever that concentration is. That goes here, and then we actually raise the coefficient out front of it as the power there. Okay, so if this is a 3, you put a 3 in here. If this was a 1, this would be a 1 over here. So it's your concentration raised to the power of your coefficient times the concentration raised to the power. Notice how it's not adding, it's multiplying the two together. Okay, do the same thing for the reactants. So you're going to divide by your reactants here. Okay, so you have your A to the A and B to the B for expression. Now, if you only have one reactant, well, then you get rid of the B. If you only have one product, well, you get rid of the D, and there's just one there. So if you have 5 reactants, you can have 5 different things you're multiplying on the bottom. Okay, as long as we're dealing with concentration for all of those different things. Okay, so let's take a look at this idea in terms of positioning. Now, if you have a small k value, so if your k value or your equilibrium constant is small, all right? If you think about that, we're taking products divided by reactants. So if mainly everything in here is reactant and there's very little product, our value for k would be very small, right? So if everything is mainly down here as a denominator and we have very little product, well, k would become less than 1 and actually would be considered a very small number. Okay, these numbers can be down to 0.000001. It can be very, very small amounts for a k value. If that's the case, then we have a small k. That would be something that would be very reactant favored. So when k is small, we have reactant favored. Now, if you have a very large k, so in this case, our orange is our reactant and our green is our product, we see in this case almost everything inside our solution here is product, so the k value becomes very large. So most of it is on the numerator side, so that becomes all your multiplying is up here, very little is reactant, so your k value will be more than 1, and that number can get very big, in the thousands and hundreds of thousands actually, in terms of your product constant. Okay? Now it is possible to have a pretty intermediate mix between the two, where some stays reactant, some stays product, and it's kind of an even mix between the two. So we had to have a deciding factor that says, well, what makes something product favored or reactant favored? So where's that break point? And the way we do it is we basically say anytime you have more product than reactant, then you have product favored. Okay? So what that tells us then, since we have a ratio of products to reactants, if we get a k value that is greater than 1, we call it product favored. Okay? If you have a k value less than 1, it's reactant favored. Well, if you're dividing products over reactants, the only way you get a k value bigger than 1 is if your products are more. If you have a k value less than 1, your reactants have to be more. Okay, so that's how we determine product favored versus reactant favored. Now, typically in chemistry, if you're processing something or trying to do a reaction, you're hoping that it's product favored because you're trying to make something happen. However, there are a lot of cases that you might actually try to be inhibiting something from happening. So maybe you're trying to stop a process from happening in terms of chemistry. Well, then you'd want to have a KEQ very small so it stays as reactant favored, okay, in terms of what we're dealing with. Later on in the unit, we'll actually talk about something called the Chatelier's principle, which is how we actually can shift these equilibriums and stress an equation to push it one direction that we want to push it, okay? Okay, so when we talk about our equilibrium position, we're talking about our K values. So basically what we're looking at is our products over reactants. And the video, I believe, cuts out halfway through and gives you kind of a black screen for a couple of different segments. So we're going to kind of try to fix that here. So make sure that we got everything on this slide. If you take a look at these different things, we're looking at our KEQ. So this is just our constant at equilibrium here. So if we have a greater than 1 value, so if we have, a bigger numerator than denominator, we have a product favored reaction. If we have a bigger denominator than numerator, then we have KEQ being less than 1 and we're reactant favored. Okay. Now you put that to play in our reversible reactions and what equilibriums are, we actually can determine our equilibrium position by looking at the concentration at equilibrium. Okay, so we're not looking at the amounts, but actually the concentration. Okay, now for gases, a lot of times when we look at our concentration, we're looking for the number of moles in whatever size vessel we have. So maybe it's a 1 liter vessel or a 2 liter vessel, whatever it is, but we're still looking at concentrations there. So to do that, we say that, if you go A to B, it's product favored. If you go A to B with a short arrow and a long arrow this way, that is reactant favored. Okay, so these are things that way that we can kind of indicate our equilibrium position by using a couple of different arrows that we also saw in our demonstration. Now, one thing we want to note is that a catalyst does not affect the amount of reactants and products present. Okay, so often students think that catalysts can shift an equilibrium, or a catalyst affects our equilibrium position, and that is not true. So catalysts only change the time needed to establish equilibrium. Okay, so can I make a note of that? The catalysts do not shift equilibrium; they only change rates. Okay. Once we get this kind of idea of what is product favored versus what is reactant favored, we then can start building our equilibrium expressions. Okay, so to build an equilibrium expression, we need to have our equilibrium constant, which is our KEQ. We know that's the ratio of product concentration to reactant concentration at equilibrium. Okay, so to build this equilibrium expression, okay, we set KEQ equal to the concentration of our products over the concentration of our reactants. And then if you take a kind of generic formula here, where the lowercase a, b, c, and d represent your coefficients, and then the a, b, c, and d in white here represent the actual chemicals. The way that we write the expression up is that our KEQ is equal to the concentration of whatever chemical is your product. So notice how C and D are our products. So concentration of C, concentration of D, raised to the power of their coefficient. Okay, so we need to make sure that if this is a 2, if C is a 2, that we square it. If D is a 3, we cube this value inside here. Okay, and these brackets are a way that we notate concentration. Okay, so make sure that we're talking about concentration here again. So this is the concentration of C to its power, concentration of D to its power. So products on top, and then repeat that idea for reactants. Okay. Now, if you only have one reactant, if there is no B, then you would just ignore that in our equation, essentially. Okay. So we have our concentration in our brackets, and these are our coefficients as we build our expressions. Okay. Now, this brings us into our practice problems and working with this. So this is where the video kind of re-picked up and started talking about it. So here in our scenario, we have N2O4, a colorless gas, and N2O, a dark brown gas. They're at equilibrium with each other. Okay, so in this case, we only have one reactant and we have one product. So in this case, our equilibrium expression is going to be really easy to write. Okay, this has nothing out front, so that's a 1. This is a 2, so we're going to square this. Okay, so first thing we want to do is write the expression for the equilibrium constant and then calculate KEQ. Okay, so here's where I'm going to stop, and I'll let you guys pick up on the other video to finish out the stuff. Thank you. So here's our practice problem now to help us out. We have N2O4, which is a colorless gas, and we have NO2, which is a dark brown gas. Okay, so you actually could visually see the equilibrium here if you actually saw this in a test tube or a flask. They are at equilibrium. We see our double-headed arrow, and our reactant is N2O4, and our product is NO2. Okay, so if we mix the two gases together, okay, we can get a relationship or a ratio. Now with gases, you can use moles or moles per liter to get your concentrations, because you're always going to capture those in some sort of volume. So in this case, we have a liter of gas is mixed. So if we have 0.0045 moles of N2O4 in 1 liter, that's a concentration, right? It's 0.0045 moles per liter. So that's a molarity. And we have 0.030 moles of NO2 per 1 liter container, so that's moles per liter. Again, it's a molarity, it's a concentration. Okay, so we want to write the expression for this equilibrium constant and then calculate what that KEQ value is going to be for us. All right, so we got to go take our products divided by our reactants. So let's set it up and let's do KEQ. So we know that our K for equilibrium is our products over our reactants. And in this case, our product is the NO2. Okay? So we need the concentration of NO2, which if we look at our work, it's 0.030. Brackets tell us concentration, so no need to label. But if you look at our balanced equation, we have N2O4 making NO2, but we're making 2 of them. Okay? So because there's 2 of them, we need to square this function right here. Okay? So we take our products. In this case, we only have one product. We have that squared. Then we have to divide by our reactants. So we're going to divide by our reactants, and we only have one reactant. So our concentration for our reactant is 0.005 4, 5. There's nothing here, which basically means it's a 1. So that's the first power. You don't need that, but I'm just showing it for example. And now we have our expression set up. So this is considered the equilibrium expression, how you express it. And then if you solve it, you're actually solving for KEQ. Okay? So take 0.030 squared divided by 0.0045. If you do that and we solve it, we'll get to our answer. Okay? So if we go back up to our screen, we see now that here's our expression, 0.030 squared divided by the 0.0045, and we get a value of 0.20. Notice, no label. Okay, make a note of that. Equilibrium expressions, they're ratios because it's molarity divided by molarity. And because it always changes with squares and cubes and that kind of stuff, there isn't one set label. So we do not label K values. Okay, so it's one of those very few times in chemistry where you do not put a label. This is no label here. Okay, so our KEQ is 0.20. Now here's a question. If NO2 is dark brown and N2O4 is colorless, okay, so your reactants is colorless and your product is dark brown, will our gas look dark brown or will it look more colorless in this case? Now it's not going to be completely clear because it's an equilibrium, so some of it is going to be of a brown color to it. So it can't be clear, but would you consider this probably a light color or very dark? Well, let's look at our KEQ. Our KEQ is 0.20. So being 0.20 means that it's less than 1. Less than 1 means that the reactants actually dominate here. Okay, so we actually have more reactant than we do product. So since it's less than 1, it's more reactant. So it's reactant favored. Being reactant favored means it's mainly colorless gas. So if we look at this through a test tube, we'd actually see that this is probably a very, very faint brown color or almost colorless because most of it is going to stay as N2O4. Okay. Now as a chemist, if you wanted to change that value, there's things we can do, and that's Le Chatelier's principle, which we'll be covering in the next segment. Okay. Now there is one little caveat here. Okay. We've been talking about concentrations, and this is where people kind of get a little bit confused in this. If we take a look at another example, the decomposition of calcium carbonate. Okay, so we have calcium carbonate as a solid decomposing into calcium oxide solid and carbon dioxide gas. Okay, if we apply the equilibrium constant we've been talking about, we would say that KEQ is carbon dioxide, there's only one of them, over calcium oxide, there's only one of them, so they're both ones, divided by the calcium carbonate, which is one of them. Here's our problem. Calcium carbonate is a solid. Calcium oxide is a solid. Okay? How do you do a concentration of a solid? Solids are just grams. There's no grams per liter or grams per kilogram. There's only one thing there. It's just grams or just moles. So there is no concentration. Because there is no concentration, they're actually not part of the equilibrium, which means they have no bearing on the equilibrium, which means mathematically we ignore them. Okay? So one of the hardest things in doing equilibrium is recognizing, do we have a solid present or a liquid? Okay? So if you look at our notes here, solids and liquids are not included in the equilibriums. They have no bearing on it. They do not mathematically change it. They actually are not part of that equilibrium because there is no concentration there. So anytime you have a solid or a liquid, you delete it from the expression. So if you wanted to know the K value for this expression, it solely would be based on the concentration of carbon dioxide produced. Okay, so only that carbon dioxide gas that's made would determine how this equilibrium is established in this process. Okay, let's jump over here. We have 3 different equilibrium expressions here I want you guys to write. Okay, so take a minute, let's pause the presentation here and write the expression for these 3 different reactions, and then we'll move forward and see if you guys can get them right. Okay, so please pause the video here. Okay, so let's take a look at these 3 different answers and see how we did. Okay, so the first one, we notice we have aqueous solution, aqueous solution, aqueous solution, and solid. Okay. We have a 1, a 1, a 2, and a 1. So those are things to make note of. So our equilibrium expression would be KEQ equals, we put a dividing line there. Our products is sodium chloride. So here's your sodium chloride. There's a 2 there, so we square it. Our other product is solid, so we don't put it in. It's not part of the expression. There is no concentration there to work with. And then we divide by the 2 reactants because they're both in solution. Now they're both 1s out front, so they both have a 1 in their expression. Again, you don't need the 1s. I put them there just to help show you where it comes from. Go down to this one. You have a solid and a gas. So just like our last example in our previous slide, the solids don't play a role, only the gas does, so your equilibrium expression is just O2 concentration. The last one again, we have a solution, we have a solution, and we have a liquid. So the liquid would be ignored. Okay, a lot of times your liquid that you're ignoring is water. Okay, a little side note that a lot of times if you have something that's in liquid form, it's almost always water that you're ignoring from expressions. So we have our product is Na2SO4 divided by our 2 reactants. The sodium hydroxide has a 2 out front, so we need to make sure that we square that. Okay? So those are our different expressions. Now if we move on and actually take some practice problems, I'm going to end the video here. And then tomorrow what we'll do, we will start with this first thing in class. We'll go over the answer keys, and I'll answer any questions you guys had on the video lecture today. Also, if you have time in class, go ahead and work on worksheet number 1, which has additional practice for this. Thank you.